to this last video for the course on subRiemannian geometry. To conclude, I will give a proof of a characterization of Carnot groups that we already discussed in a previous video. There is an axiomatic presentation of Carnot groups from the point of view of metric geometry. In fact, Carnot groups can be presented as the only locally compact and geodesic metric spaces that are isometrically homogeneous and self-similar. The proof of this fact will rely on three theorems: Mitchell theorem, Berestovsky's theorem, which we discussed in this course already, plus there will be one more theorem coming from the theory of locally compact groups. And this theorem is very deep, and I will not prove it. In the lecture notes, you can find some references to other books that contain the proof. Okay, let's go. We're going to prove the following theorem. So Carnot groups equipped with their sub-Finsler structure, so equipped with their sub-Finsler distances are the only metric spaces, namely up to isometries, that have the following four properties. They are locally compact, they are geodesic metric spaces, they are isometrically homogeneous, namely the group of isometries is acting transitively. And the last one, let me call it self-similarity. So they are self-similar in the sense that they admit at least one dilation. Okay, let's check that it's clear that Carnot groups have these four properties. So one direction is clear. So, but let's check it. So, if G is a Carnot group, then okay. So, in particular, this is a Lie group, so it's a manifold, and therefore it's locally compact. And one is proved. Then, what are other properties? So, it's a Carnot-Karateodori space. Plus has the structure of Lie group, and therefore it's not just a length space, it's really a geodesic space. So it's geodesic. And this was the second property. Then all the geometry is left invariant. So left invariance implies that this is an isometrically homogeneous space. And actually, regarding the dilations, on Carnot groups, we really have this map that we call delta lambda, that are delta dilations. And we actually have this for all lambda in zero infinity. So it is self-similar. And in the assumption of the theorem, we'll now only assume that there exists one dilation, and then as a consequence of the theorem, we will have that the space admits dilation of every factor. Okay, so Carnot groups admits these four properties. Let me clarify that if you remove each of the four, that you have other things except Carnot groups. Just let's do it as a small exercise. So let's remark that each of the four properties or conditions are necessary to define Carnot groups. Otherwise, one can consider these following examples. So if you remove one, namely locally compactness, you can take also every infinite dimensional Banach space, check that you have still the other three properties, namely geodesic, isometric homogeneity, and dilations. Then without the second property, one can take what are called snowflakes of metric spaces, namely take a space that has that is a Carnot group, and take the power of the distance with an exponent that is less than 1. For example, one can take R with distance square root of x minus y. This is a function of x and y. So these are called snowflakes. And now this is not a geodesic space anymore, but still it's isometrically homogeneous, locally compact, and admits dilations. Without 3, one can take cones. So one can take every cone with angle, of course, different than 2 pi. Otherwise, you get Rn. And then without 4, one can take every compact Riemannian group, for example, S1. Okay, so now that these properties are a little bit more clear, let's start with the proof. Okay, proof of the characterization. Now, I will prove the theorem modulo 3 other theorems. Okay, so it will be, the proof will be easy, will be an easy consequence of 3 hard theorems. Okay, what are these theorems? The first one is a new theorem. I never discussed this in the course. It's a theorem, quite famous theorem, due to Gleason, Montgomery, and Zippin. This is a theorem that is one of the consequence of the solution of the Hilbert fifth problem. So it's a quite deep theorem. And it follows from all this study of locally compact groups and their structure, and the structure of groups, topological groups with no small subgroups. Okay, so the theorem is the following. Suppose you have a metric space, and assume that you have this property. Suppose that it's connected, locally connected, and has finite topological dimension, and it is isometrically homogeneous. So suppose you have these 4 properties, then the isometry groups, the group of isometries, which is when it's equipped with the compact open topology, is a topological group that is locally compact. In particular, in this case, has the structure of Lie group. The isometry group is a Lie group. So I'll use this theorem in the proof. A second theorem that I will use is a theorem that we already discussed in the course, is theorem due to Berestovsky. It's discussed in the previous video. I'm putting the date of the English publication on the publication written in English. It originally was in Russian. So suppose you have a Lie group and you have a subgroup, a closed subgroup. So the quotient becomes a manifold, and suppose you have a distance function dismetrizing the quotient. So induce the manifold topology. Assume that this distance d is geodesic. Maybe I should have clarified. I said it's also the G invariant. So G acts on G mod H, leaving this distance invariant. Then the space G mod H with this distance is a Carnot Theodori space. In other words, the distance is a sub-Finsler distance. Another theorem that we will use and we discussed previously in this course is a theorem attributed to Mitchell from 1985. That says that you can take metric tangents of equiregular Carnot Theodori spaces and get Carnot groups. Okay, so let's now take this theorem for granted. So in previous video, you find a discussion on these two theorems. But now we take all the three theorems and we will prove that if you have a metric space that has the fourth property, let me recall the property. You have local compactness, you have geodesic distance, you have the space is isometrically homogeneous, and you have self-similarity. Then we need to prove that the space is a Carnot group. Okay, so let's start building some differentiable structure, and for this we will use theorem 1. So we need to check those properties. So the properties were, I recall, is connected, locally connected, isometrically, no, the first was finite topological dimension, and isometrically homogeneity. Okay, so our space is assumed to be a geodesic space, and therefore it's connected to curves, so it's path connected. And also balls are path connected, so it also becomes locally connected. Okay, so these two are done. Isometrical homogeneity is also assumed. So we don't need to do any proof for that. Now, why our space have finite topological dimension? This is quite interesting. So why is X of finite topological dimension? All right, we need to prove this. And I'll prove something metric. I'm going to prove this claim. I'm going to prove that X is a doubling metric space. What does this mean? This means, I recall, this means that there exists a constant C such that for all points in the space and for all radii, each ball, fix P and Q, so I have to say the ball in X, center P, radius R, this can be covered with a number bounded by C, so C many balls of radius half of the radius, so R over 2. Okay. We want to prove this property. Okay. So what we will do it for a given point and a given radius. And for this, we will use local compactness. And then we will just use homogeneity and self-similarity to get for every point and every radius. So that's the plan. So let's start. So indeed. So pick any point P0 in X. And then take R0 such that the ball B in X, P0, R0 is precompact. I'm thinking the balls are open, or you can work with the closed balls and say that the ball is compact, okay? And this R0 exists since X is locally compact. Okay, now let's also, we don't have dilations for every factor, but we have one. So let's fix one of the factor. So we fix some lambda. We can assume that it's in 1 infinity, so it's greater than 1, such that there exists a lambda dilation on X. If you have a dilation with a factor smaller than 1, you can just take the inverse map. Okay? And that's going to have factor greater than 1. Okay? Now, since, so we said that the ball B, P0, R0 is precompact, then the ball P0, R0 can be covered with finitely many, say C, balls of radius. Now I can put any number smaller, actually any number, right? So I fix this quantity. Now the balls with this radius, they form a cover of this closed ball. Okay? So I can just, since this is the closed ball is compact, I can we can select finitely many that cover. Okay. Now let's use now the homogeneity. Now by homogeneity, for all the same holds for not just at P0 but any other point. For all P in X, B, P, same radius R0 can be covered with C many balls of radius R0 over 2 lambda. Okay, now let's take an arbitrary radius. So let R greater than 0. Now take M, an integer, such that lambda M R is less than R0 is less than lambda M plus 1 R. Okay. So So in particular, we have that the ball with radius lambda m r is contained in BP R0 because of this inequality. Now we know how to cover this ball. Let's use the same cover to cover this other ball. So this possibly smaller ball, P lambda m r, can be covered with C many balls of radius was R0 over 2 lambda. But also we can take a even larger radius for this ball. Take the same ball but with a slightly larger radius, but with the radius. So I will use now this inequality here with radius lambda m plus 1 r divided by 2r, which is lambda m r divided by 2, which is bigger. It's a bigger radius, so it's still good. Excellent. Now what we do, so we covered this ball with the balls of this radius. Now we apply the dilation. So now apply dilation m times. And what we get BPR can be covered with C many balls of radius R over 2. Okay. So we proved that X is a doubling metric space. Now, what one can prove is that doubling metric spaces really admits a measure or like the that makes them alphas regular, and equivalently one can prove that that the spaces are alphas regular and their Aswad dimension is finite. So let me just write here that X has finite Aswad dimension, and as a further consequence, one has that X has finite Hausdorff dimension. Now, these consequences are standard fact in analysis of metric spaces. Okay, now the Hausdorff dimension is always greater or equal than the topological dimension. So X in particular has finite topological dimension. And this was what we wanted to prove. Okay, in total, what we checked is that X satisfies the assumptions of the first theorem, theorem 1, Gleason-Montgomery zipping. And therefore, the theorem says that the isometry group of X is a Lie group. And moreover, this group is because it's isometrically, the space is isometrically homogeneous, this is acting transitively on X, which now becomes a manifold. Okay, so this implies that X has the structure of manifold G over H one can take G to be this isometry group, and H the stabilizer of a point in G, 0, G. And this group is a closed subgroup. Actually, in this case it's really compact. The isometry fixing a point by a scalar ZL is a compact space. Okay, so now this becomes now a manifold, and it's homomorphic to X, and G is acting smoothly. Okay, so we got the group structure. So now I will write G mod H instead of X. So what we have is that now we have the space. So X XD is equal to G mod HD, and this space satisfies the assumptions of theorem 2, Berestovsky, namely it's a manifold of the form G mod H with a G invariant distance that is geodesic. Okay, up to now we didn't use the fact it was geodesic except to say that there was a connected, a locally connected metric space. Okay, so second theorem says that this space it's a Carnot Karateodori space. Now, the fact that we have a homogeneous structure implies that the Carnot Karateodori structure is equiregular. And therefore, by Mitchell's theorem, theorem 3, we have that the tangents of this space, G mod H, are Carnot groups. All right, now we will use the fact that the space admits dilation to say that it coincides with its own tangents. Since XD admits some lambda dilation for a given lambda, then XD is isometric to X lambda D. This is the same of saying admits an isometric, admits a dilation. Means that these two metric spaces are isometric. And we can iterate, right, the map. So we can say X lambda to the N D is still isometric, okay? Now, as N goes to infinity, right, so we're assuming lambda greater than 1. Okay, so this number goes to infinity, correct, okay. Now, this sequence of metric spaces, which is actually constant, but this sequence of metric spaces converge by definition to the tangent, or to a tangent. X lambda N D, this converge to a tangent, and in this case we know it converge to a Carnot group. But this sequence is constantly equal to X, and therefore we get that this Carnot group is isometric to X. In conclusion, X is a Carnot group. And this consequence completes the proof of the theorem that was characterizing Carnot groups as the only metric spaces that are locally compact, geodesic metric space, are isometrically homogeneous, and admit at least one dilation. Okay, so this series of videos on subRiemannian geometry finish with this one. Thanks for watching. I hope you like the course and that this course raise your interest in subRiemannian geometry. If you want to continue to study Carnot characterizatory spaces, you may contact me. In any case, I hope to see you again, hopefully in person. Bye-bye.